Alright, so in this video we will be looking at the reduction of aldehydes and ketones. This requires a strong reducing agent such as a hydride, and so we have a couple of different choices of reducing agent. We have sodium borohydride in do this with water or an alcohol, or we can use lithium aluminum hydride in diethyl ether, and both of these reducing agents should give us the alcohol. So now these two reducing agents have different strengths. One of these reagents will be stronger than the other, and that is the lithium aluminum hydride. So if we look at different carbonyl compounds, the carboxylic acid, the ester, ketone, and the aldehyde, and what we'll see is that sodium borohydride is capable of reducing ketones and aldehydes, while lithium aluminum hydride is capable of reducing all of these carbonyl compounds. In fact, lithium aluminum hydride is so much more reactive than the sodium borohydride that if we were to use water or an alcohol as our solvent with lithium aluminum hydride, it would explode. So remember, we need to use ethers as our solvent with lithium aluminum hydride, something that does not contain an acidic proton, that can react with the lithium aluminum hydride and cause an explosion. So the mechanism behind this reaction is essentially a nucleophilic addition to the carbonyl, except that our nucleophile will be a hydride. So if we start with a ketone, and we have the borohydride here, then one of these boron-hydrogen bonds, the electrons from this bond, can attack this partial positive carbon and kick the electrons up to that oxygen. Now we have a negatively charged oxygen and a proton attached to that carbon. So now it's just a matter of protonating the oxygen, which we can do with water. And we can convert our ketone to a secondary alcohol. So another way that we can reduce carbonyls or aldehydes and ketones is through catalytic hydrogenation, similar to catalytic hydrogenation of alkenes. And so if we take another ketone, we react that with hydrogen gas in the presence of palladium on carbon or rainy nickel, then we can reduce this carbon-oxygen double bond to a carbon-oxygen single bond, and again convert our ketone to an alcohol. And we can do this with aldehydes as well. The one thing we have to remember is that the carbonyl bond is less reactive towards hydrogenation than carbon-carbon double bonds. And so what that means is if we have a molecule where we have both a carbon-carbon double bond and a carbonyl, then if we're using catalytic hydrogenation, that carbon-carbon double bond will be reduced first. So as an example of that, we use this molecule here, with a carbon-carbon double bond and a carbon-oxygen double bond, so we have an alkene and a carbonyl. If we use one equivalent of hydrogen gas, one equivalent hydrogen, in the presence of a palladium on carbon catalyst or a rainy nickel catalyst, then we'll preferentially hydrogenate this carbon-carbon double bond while keeping that carbonyl. And so this will be our major product. If, on the other hand, we use excess H2 and either a palladium on carbon catalyst or a rainy nickel catalyst, then we'll hydrogenate both double bonds and convert the ketone to the alcohol. However, if rather than using catalytic hydrogenation, we were to use sodium borohydride as our reducing agent, using, let's say, ethanol as our solvent, then we would preferentially reduce that carbonyl to the alcohol while keeping the carbon-carbon double bond. So this reduction, whether we use lithium aluminum hydride, sodium borohydride, or catalytic hydrogenation, this reduction has an effect on the stereochemistry, because our carbonyl is sp2, and so it's trigonal planar. Now that means that the nucleophile, our hydride, can attack from the bottom or it can attack from the top. And depending on the orientation of the molecule when the nucleophile attacks from either side, then we'll get 2 enantiomers of product. And so we'll say that with the addition of hydride, we can have this alcohol with the hydride added to the bottom, or we could have this alcohol with the hydride added to the top. So we can have 2 different enantiomers. And an example of this, if we use an ethyl methyl ketone, react that with sodium borohydride in water, for example, then we can get the 2 enantiomers of the alcohol. So that's important to remember, that we're going from a trigonal planar shape to a tetrahedral shape, and so we can introduce stereochemistry into the molecule. With these simple reducing agents, we can't really control the stereochemistry. We'll wind up with a racemic mixture. But there are chiral reducing agents that can be used to preferentially produce one enantiomer over the other. And so what if we, instead of wanting to reduce an aldehyde or a ketone to an alcohol, let's say we wanted to reduce a carboxylic acid to an aldehyde. Well, we can sort of do this using a strong reducing agent, such as lithium aluminum hydride. The problem is lithium aluminum hydride and any other reducing agent strong enough to reduce this carboxylic acid will also reduce the aldehyde, because the aldehyde is easier to reduce than a carboxylic acid. And so the reaction will go right through the aldehyde to the alcohol. So yeah, that would also be lithium aluminum hydride. Then we wouldn't be able to stop it at the aldehyde. The reaction would just go right to the alcohol. And so if we want to convert carboxylic acids to aldehydes, what we have to do first is to convert the carboxylic acid to something that can be more easily reduced, and then use a weaker reducing agent. And so let's show how that might be done. And we'll discuss how to convert the carboxylic acid to these other molecules later. And so we have acyl chlorides, esters, and nitriles. That these 3 groups can all be created from carboxylic acids relatively easily, and then we can reduce all of these to the aldehyde using weaker reducing agents, such as lithium, aluminum, tritert butoxy at negative 78 degrees C, or dipole H again at negative 78 C, so and all of these reactions will produce the aldehyde. So what makes these reducing agents weaker than the other reducing agents we've looked at so far is steric hindrance. That the lithium So our lithium aluminum tritert butoxyhydride has a structure, it's an ionic compound. Has these bulky tert-butyl groups surrounding the aluminum, so that it's difficult for this reagent to access the carbonyl very easily, and so this has limited reactivity. That dibol H is similar. Dibol H is di-isobutyl aluminum hydride. And it has these two isopropyl groups attached to the aluminum, so that it also creates steric hindrance and makes it more difficult for this reagent to access the carbonyl. And so the steric hindrance makes these compounds into weaker reducing agents. And so if we look at some of the mechanisms by which we can, by which these reagents work, if we start with an acid chloride, so we'll look at the conversions of acyl chlorides to aldehydes. That first the oxygen reacts with aluminum, not aluminum, lithium, because we're using the lithium tritert butoxy aluminum hydride. So the oxygen reacts with the lithium and produces this organolithium complex. Then once we have this positive charge on the oxygen, it's going to pull additional electron density away from this carbon, making this carbon more partially positive, and that allows that allows the electrons from this aluminum hydrogen bond to attack that carbonyl carbon and kick the electrons up to that positively charged oxygen. And it forms this tetrahedral intermediate with this oxygen lithium bond still present. Then we have this hydrogen attached to a carbonyl carbon, and we still have this chlorine attached to that carbonyl carbon. So in the next step, the lithium oxygen bond, these electrons will attack the electron deficient aluminum, forming this oxygen aluminum bond. And once we have this this oxygen aluminum bond, then the electrons from this oxygen can also come down to this carbon and kick off the chlorine. And so this gives us this oxygen aluminum complex with the negatively charged aluminum, positively charged oxygen, that I won't draw the rest of this mechanism, but we add water, and there will be several steps involved, but it liberates the aldehyde, and it breaks that oxygen aluminum bond and liberates the aldehyde. So that's how we can go from an acyl chloride to an aldehyde using the lithium tritert deoxyaluminum hydride. And that the mechanism for converting an ester to an aldehyde is not too different. Instead, we use diol H as our reducing agent. Our carbonyl oxygen will attack the aluminum. Then the aluminum hydrogen bond, those electrons will attack the carbonyl carbon and kick the electrons up to that carbonyl oxygen. And once we get this intermediate, then again The rest of the mechanism is a little complex, but we just add water. There'll be several steps, and we lose our alcohol. This OR gets lost as an alcohol and will form the aldehyde. So the last mechanism that we'll show is the conversion of nitriles to aldehydes. That in this case, we're still using dibol H. And our lone pair of electrons on this nitrogen will attack that aluminum. And once we have this nitrogen-aluminum complex formed, the aluminum-hydrogen bond, these electrons will attack that nitrile carbon and shift the electrons over from this triple bond to this nitrogen. So that triple bond becomes a double bond. And we still have this nitrogen-aluminum bond, and again, we add water, and there'll be several steps to convert this complex to the aldehyde. So that's a brief introduction to the reduction of carbonyls and the reduction of aldehydes and ketones to alcohols and the reduction of carboxylic acids to aldehydes.